Now let us consider the flow of steam through a convergent divergent nozzle itself. Now it's like this. Steam a convergent divergent nozzle. Now the flow is adiabatic and no work is also involved. Flow is adiabatic, and no work is also involved. Also note there is also no potential change, potential energy change took place. Thus, it is only a steady flow energy equation. Thus, the steady flow energy equation, flow energy equation become H0 plus V0 square by 2 equal to H1 plus V1 square by 2, which means there is all the other energies are negligible except the enthalpy of the incoming jet and velocity of the incoming jet, which is supposed to be or kinetic energy or internal energy plus kinetic energy of the incoming jet is equal to the internal energy or kinetic energy of the outgoing jet, provided there is no such loss anywhere during the work itself. Now, if the velocity of the approach or incoming velocity is too small, and the velocity of the exit from the nozzle can be given by the following formula. If the velocity at the of the incoming nozzle is very small, then the velocity at exit, then the velocity at exit will be given by the at exit is given by the following equation V1 by the equation V1 equal to 2 into H0 minus H1 multiplied by 10 to the power 3 to the power half, means square root, which is equal to 44.72 H0 minus H1 to the power half in meter per second. So what we have here? We have the change of enthalpy, internal energy. The rate of change of internal energy is multiplied by 10 to the power 3, which is converted into joules to the power, so it's a square root, or whole square root. Thus gives us the velocity inlet of the inlet velocity itself, where H0 H1 is the enthalpy drop across the nozzle. So H0 minus H1 H0 minus H1 is the enthalpy drop. Enthalpy drop across a nozzle. Now, the isentropic flow, we know we have an equation called isentropic flow. We have this following equation T ds equal to dH minus VTP equal to 0, or we know that is isentropic, so dH should be equal to 0 as ds is equal to 0. The equation will take the form integration of 0 to 1 dH is equal to integration of 0 to 1 VTP. Now, or if we change this like this, H01 and H0 minus H0 minus H1 is equal to minus 0 to L VTP. Now, this equation, from equation number 22, this equation you know from this equation itself, H0 minus H1 is equal to V1 square minus V0 square whole square. So, we can simply write as H0 equal to H0 plus V0 square by 2 is equal to H1 plus V1 square by 2, or H0 minus H1 1 equal to V1 square bar by 2 minus V0 bar by 2, or which is equal to minus 0 to L the total length VTP. Now, the pressure and volume of the stream during the expansion to obey the PV to the power n constant. The pressure and volume, the relation between pressure and volume of the tube volume of the reciprocal pressure and volume of pressure and volume of a gas of steel during the expansion obey the hollow. During expansion obey the law P to the power gamma equal to constant. Now, where K is the isotropic index itself, K isotropic index. Now, at neglect the index velocity V0, if we neglect inlet velocity, V0, just 1 second please. Neglect index V0, then V1 will become, and V1 dash by 2 will be just equal to minus integration of 0 to L and P0 V0 to the power K to the power 1 by P0 to the power K whole to the power 1 by K, and P is equal to the power minus 1 by K dP is equal to dP, or Pv to the power K, or minus 0 to L P1 K into P1 K multiplied by 1 by K itself. Now, Pv to the power K Pv to the power K 1 by K is equal to P minus 1 by K is equal to dP, or this is equal to K divided by 1 by K by 1 minus K multiplied by P0 V0 minus P1 V1 neutrality. Now, if we write the equation like this, K by K minus 1 multiplied by, if you got P0 V0 outside the bracket, P0 outside the bracket, then that is equal to 1 minus P1 by P1 by P1